We're going to take a look at this thing called transformations of our quadratic graphs. And basically what we're going to do is we're going to take the standard y equals x squared and we're going to move it around. By the end of this video, you should be able to know how you look at an equation and determine if the graph had been moved up or down, left or right, if it had been flipped or reflected about the x-axis, or if it has been stretched to made either a little bit skinnier or a little bit wider, or a combination of all of these things. So I'll display this at the end, and you should be able to have an idea of exactly what to look for to spot those things in the equation. You'll see that I'll be using this note sheet, which is attached to the lesson plans, and there's a lot of text on this note sheet that I'm not going to read through in the video because you can read through that. But this, if you read the text, watch the video, look at these examples, write them down yourself, you're going to understand those transformations pretty darn easily. This is the parent graph. The graph you're looking at right there is the good old y equals x squared, and it's called the parent graph because it's kind of the base graph, and all of the other movements that we do are going to be related to the original starting point of y equals x squared, the parent graph. This would be an excellent thing for you to use Desmos on, because if you're following through this text, if you go to Desmos, you can type in any equation and instantly see how the equation makes the graph look differently. So let's get going right away. The first thing we're going to look at is what happens if you want to translate or have a transformation of your equation, your graph, upward or downward. And so I have three different graphs here, and you notice that compared to the parent graph, they've all moved slightly. It's worth noting that the actual parent graph would always be sitting like right there. I'm not going to draw it too large because I don't want it to take over the picture. But I've just drawn the parent graphs. And if I took this original parent graph y equals x squared and moved up 4 units, beep, 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 I've now translated my equation 4 units upward, and y equals x squared plus 4 is the equation that gets that done. Notice this one has gone a translation 5 units downward. X squared minus 5 is what did it. This is x squared plus 2, and the parent graph went up 2. So it's pretty easy to see that when you add or subtract a number to your x squared, you're going to move your graph upward or downward. That's how you do the translations up and down. So of those items that we're looking for, we already know number one, just move up or downward by adding something or subtracting something to your x squared. So when I do y equals x squared minus 5, I've just moved the parent graph, the vertex of the parent graph, 5 units downward. Let's take a look now at how would we translate something to the left or to the right. And we've got 3 examples down here. And now notice these equations, they definitely look different. Here's a minus 4, but that's inside the parentheses. Here's a plus 2, and here's a minus 1, but they're inside the parentheses, which is very different than what we had before, where the plus or the minus was kind of separated from the x. Well, this is how we move a translation to the left or to the right. Remember, your parent graph was right here, and in this case it got moved 4 units to the right. We have a translation of 4 units right. Well, you have to be very, very careful, because if you look at the actual equation, we have a minus sign. So that goes against your intuition. But when you move things left or right, it is the opposite of the x plus or the x minus the number. For example, this was x plus 2. Your instinct would say I moved 2 units to the right, but I actually moved 2 units to the left. X minus 1, 1 unit to the right. So on your note sheet, the text down here sums that up. But basically now we have 2 things to look at If something is added or subtracted to the x squared, that's moving it up or down. If something is attached to the x inside the parentheses squared, that moves it left or right. And be careful, your instinct could be wrong. A -5 means we've moved it to the right 5. The equation down here at the bottom of your notes shows you that you can do 2 moves all at once. The -3 inside the parentheses attached to the x means I'm going to move my vertex 3 units to the right. The -5, kind of on its own, means 5 units down. So if you take a careful look at where the parent function originally was, which is always right there, and you think just about the vertex, that's the easiest point to work with. The vertex is 0, 0. Let's move it right 3 units. So I go beep, beep, beep. Now my vertex would be sitting right there at x equals 3, y equals 0. But now I move it 5 units downward. Beep, 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 beep. And there's my new vertex at 3, -5. So you can definitely combine your left, right, up, and down. We're going to head over to the other side, but I'm going to spill the beans right away. The other side of the notes is what I was referring to. We can flip a graph by simply attaching a negative to the x squared part. So here's what I mean. On the other side of the notes, here's your parent graph. And if I just take y equals x squared and call it y equals -x squared, my graph looks like that. Don't believe me? Check out Desmos. So all this is doing is, the fancy terminology would be reflecting the graph about the x-axis, but you can just think of it as flipping it from positive territory to negative territory. And by the way, the same thing could happen if you had a fancier graph, like if I had x plus 3 squared, you know that that would mean we've translated the parent graph 3 units to the left, so it would look like that. But if we decided that we wanted to do a reflection or a flip, I'd put a negative on that, and the negative would just make it look like this. So remember, I can always now start looking right at an equation, and I don't even have to go through the t-chart process. I just say, from my parent graph, I move 3 units to the left, and I reflect it about the x-axis. Beep, 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 3 units left, and then make it open downward. Sometimes we will call this opening downward, whereas this might be called opening upward. Okay, this next part and the last part of the new learning is what's called the vertical or horizontal stretch, but you might want to think of it as the graph getting skinnier or wider. So think of your parent function, y equals x squared, having kind of a standard width. As soon as I add a coefficient, here's a 0.25, so it's smaller than 1. Here's a 5, that's bigger than 1. Remember, the parent graph has a coefficient of 1. So when I make my coefficient bigger or smaller than 1, I affect the width of my graph. And here's how it goes. If my coefficient is bigger than 1, like a 3, an 8, or a 5, my graph gets skinnier. They call that a vertical stretch because they say, kind of imagine taking your parent graph and stretching it upward. Anytime my coefficient is smaller than 1, then I get a wider graph, and that's called a horizontal stretch. So imagine taking your parent graph and just kind of stretching it horizontally or wider. So if you look at your coefficient, you will now know a little bit about how wide your graph is. If I want my graph to be skinnier, I make this coefficient larger than 1. That's called the leading coefficient, by the way. If I want my graph to be wider, I make that leading coefficient less than 1. And by the way, in standard form, which we learned very recently, the leading coefficient that we're talking about is the A value. So here's where we should stand I know you had a lot of information thrown at you, but once your brain has the chance to digest this, you should be able to look at any of the equations that you see here, even as complicated as this, and know how to take your original parent function and make your translations left, right, up and down, flipped, wider, or skinnier based on what you see in that equation. You can also use your friend Mr. Desmos to help check yourself because it'd be easy to type these equations in and graph them. Once again, this is the summary. Everything you're looking at here is what needs to be installed in your brain once you've done some practicing of this homework.